You'll notice in exercise 1716 that your reactant, so they say propose a mechanism for this transformation, you notice that the reactant has but one ring, and the product has 1, 2, 3 rings. You've made rings, and so the only way we've learned how to do that so far is with the Diels-Alder reaction. So at least you see the extra rings you've made, and you should think Diels-Alder reaction. Well, you know that for a Diels-Alder reaction, you need a diene, and here I'll sort of put that in blue, that diene, and you also need a dienophile, which is going to be a double bond all by itself, a little further away. And you'll notice this has an electron withdrawing group on it, like we've seen in the simpler Diels-Alder reactions. This, by the way, is a beautiful exercise because rings like this are formed a lot in living things. Living things ultimately make cholesterol, which has a whole bunch of rings like this. Cholesterol has this sort of repeating ring structure. And then all of your gender hormones, like testosterone, progesterone, estrogen, those are made from cholesterol. They all have that ring structure. All of those molecules are made ultimately from linear molecules in living things. Your cells use linear molecules to make those big rings, and they do reactions like this to do that. So this is a really good preparation for biochemistry, understanding how living things can take stuff that seems to us as so obviously inorganic and turn it into molecules that are so clearly a part of life. So we have our diene in blue and our dienophile in orange. Now the other thing you would want to notice here is that you have is the part of these molecules that overlap. So imagine you have this shape here. You have this shape, and that shape is matched here by these atoms. So the rest of the atoms must have curled in on themselves. Let's number these. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So if we do that same thing over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So we can redraw this molecule on the left, but we're going to redraw it in such a way that the bond between carbon 10 and 11, instead of going to the right, rotates so that chain is going up. So we'd have 8 here, then 9, 10, and now we want to go up to 11. And now we're going to go over to 12, down to 13, up to 14, and then we'll have 15 and 16. So really we've taken this molecule on the right, our product, and we've drawn it just without forming the rings themselves. So we have this molecule on the left, and we'll fill in those bonds there. So between 1 and 2 we have a pi bond, 3, 4, 5, 6 is where we have an oxygen. So got an oxygen at 6. Between 7 and 8 we have another pi bond in this structure here. The next thing we should run into is at carbon 13. Between 13 and 14 we have another pi bond. And so that would be the last of it. So we have that ketone at 15 and then the 16 hanging out at the top. And you'll see here that if you curl that molecule back, this straight chain back around by rotating a couple of those single bonds, that we have a pretty nice setup for a Diels-Alder reaction. So let me erase these numbers that we were using just to make sure that everything was attached in the right place. And now let's number this chain so that we can see the diene and the dienophile. So here, this would be the conjugated pi system, 1, 2, 3, and 4. And then we have the diene on the other side, so like 5 and 6. We would draw our little dots at the end of the conjugated pi system and at the end of the dienophile, and we'd draw dotted lines in between those. And then you would move each of those pi bonds around. I'm going to move them around clockwise. So notice when you do that, in here, I'll just color these pi bonds so we can keep track of them a little bit more easily. Actually, let me these, and then blue one here. So we're going to take that blue one on top and we're going to move it between carbons 4 and 5. So this bond right there, that's going to move between 4 and 5. We're going to take the green one, and that's going to go between carbons 2 and 3. And we're going to take that purple one, those purple pi electrons, we're going to move that between carbon 1 and 6. And you can see that that gives us the product that we have, above. So for me, you don't have to worry about the stereochemistry, but you can see how you can form those rings by doing an intramolecular Diels-Alder reaction. So the diene and the dienophile are both in the same molecule, and that lets you form multiple rings all at once.